Hello, Black Hat. Nice to meet you. Let me introduce myself. My name is Sergey Puzankov. I work at Positive Technologies as a telecom security expert. Today, I will tell you about the results of our recent security research on mixed-generation mobile networks. First of all, let me introduce the team without which this research would not be possible. These are Sergey Mashukov, Alexander Onegov, Pavel Novikov, and myself. All these guys have great skills and enormous experience in mobile security realm. I'll talk about vulnerabilities in signaling protocols, so a few words about what signaling networks are. Nowadays, mobile networks use three general signaling systems for interoperation between operators: SS7, Diameter, and GTP. SS7 is a set of protocols, not just one. It is primarily intended to set up and tear down telephone calls. Later, when mobile telephony appeared, SS7 began to be used for subscriber mobility, roaming, short messages, and other services. Diameter is originally an authentication, authorization, and accounting protocol. However, this protocol is extensible. RFT 5516 is an example of an extension. This RFC defines a set of command codes used in applications for the Evolved Packet Core. Evolved Packet Core is a switching system of LTE networks. GTP is a group of protocols that were developed to control packet data services on GSM networks. However, later GTP was adapted to work on UMTS, LTE, and even 5G networks with non-standalone architecture. Signaling protocols are used between network elements on operators' infrastructure, not on the user side. The basic unit in signaling is a message or a signaling message. This is like a packet on IP networks. I will use the term message throughout the presentation. Please bear in mind that when I say message, I mean not an SMS message, but a signaling message. When an intruder gets access to the signaling network at any telecom operator, that intruder can track locations, intercept SMS and voice calls, performs denial of service attacks on subscribers and home networks, steal money from subscribers, get access to email, social media, mobile messenger apps, and other applications. Intruders are able to do all these malicious actions against any subscriber of any mobile operator around the world from any signaling connection. Why are signaling networks insecure? When the SS7 protocol stack was developed, nobody thought about security, because SS7 networks were originally intended to support telephone calls only. They were assumed to be isolated from other public networks. Only a few large national telephone providers would have access to SS7. But later, mobile phones appeared. The number of players on the telephone market rapidly increased. The number of users jumped, and consequently, the amount of signaling grew enormously. In the early 2000s, a new specification called SIGTRAN was introduced. SIGTRAN allowed sending SS7 over IP networks. So, those two main assumptions underlying signaling security were no longer true. The number of companies connected to signaling networks became huge, and the signaling networks stopped being isolated. New protocols such as Diameter and GTP didn't solve security either. In fact, they brought new problems. Fortunately, mobile operators are aware of the signaling security problem and are trying to protect their networks. They implement signaling firewalls, SMS home routing, and signaling IDS systems. Also, mobile operators perform external signaling security assessments. However, sometimes this is not enough. Now I would like to describe the basic identity and node types on mobile networks, because I will also refer back to this information throughout the presentation. The first group of identities and nodes is used on 2G and 3G networks, such as GSM and UMTS. MSSDN This identifier with a long acronym is just the phone number we all use to call our friends. IMSI, International Mobile Subscriber Identity. This is the identity of a SIM card. GT, a global title. This is the main address of the core node on telecom networks that looks like the MSSDN or telephone number. The GT and MSSDN have the same structure. Network elements route signal messages, but they are GT and MSSDNs. I should also note that the MSSDN and IMSI are used in all mobile generations. STP, Signal Transfer Point. This is a switch for signal traffic. Usually the STP is a border point on a mobile network. HLR, Home Location Register, is a subscriber database of a mobile operator. It contains the following data: MSSDN and IMSI identifiers of subscriber, allowed and prohibited services, addresses of nodes serving the subscriber, and certain other data. MSC VLR. This is a single node that performs two functions. The MSC, Mobile Switching Center, is a switch for voice and SMS traffic. The VLR, Visited Location Register, is a database of active subscribers that contains copy of subscriber profiles from the HLR, plus some information from the radio access system, such as the identity of the serving cell. SGSN, Serving GPRS Support Node. This node performs the same function that the MSC VLR does, but for packet data services. And SMSC, SMS Center. This node handles sending and delivery of short messages. GSM and UMTS networks rely on SS7 signaling. As I previously said, SS7 is a stack of protocols. I will highlight the most important protocols in it from the security point of view. The lowest layer that works on the international level is the SCCP, Signal Connection Control Path. This protocol is responsible for global routing of signaling messages by telecom-specific identifiers, which are called global titles. The TCAP protocol is located above the SCCP. This protocol combines single requests and responses into dialogues and defines the context of the upper layer application. The mobile application part, or MAP, is a payload that contains the code of a particular operation and relevant parameters. IMSI, location information, profile data, and so on. The second group of nodes is used on 4G networks, such as LTE. DA, Diameter Edge Agent. This is a switch for signal traffic. Usually, the DA is a border point on a mobile network. It works like an STP but on diameter networks. HSS, Home Subscriber Server, is a subscriber database of a mobile operator. The HSS is an evolution of the HLR applicable on LTE networks. MME, Mobile Management Entity, supports mobility management procedures for mobile subscribers and is responsible for choosing the SGW. SGW, Serving Gateway, is a switch of user data packets. IMS, IP Multimedia System. This is not an LTE node, but an independent system responsible for standardization of voice calls on IP networks. IMS is often used on LTE networks as an extension for voice call transmission. Diameter, the signal protocol for LTE networks. This protocol is IP-based. The transport layer protocol is SCTP. This protocol was developed specially for telecom applications. Finally, the top layer is diameter itself, with a command code, application ID, and other parameters. GTP is a group of protocols. It is divided into three protocols. GTPC, the control part, is used for signaling. GTPU, the user part, is used for tunneling of user data. And GTP prime is used to charge user traffic. As I previously said, GTP is used on both GSM UMTS and LTE 5G networks. I also described SGSN and SGW nodes. GGSN and PGW are gateways between the mobile operator and external internet. GTPC is also an IP-based protocol. It utilizes UDP as a transport. The GTPC payload is located just above UDP. Mobile networks have evolved. These days, they combine several generations. So that mobile subscribers have seamless service, the home subscriber databases are joined. Mobile networks of new generations, such as 4 and 5G, must have connectivity to previous generation networks. For this purpose, IWF, interworking function equipment, is used. It allows relaying SS7 messages to diameter ones and vice versa. A mobile device on the combined networks is connected simultaneously to all possible generations. When a mobile device is somehow disconnected from one of the networks, it still remains online via other network generations. Having performed signal security audits since 2015, we have gathered interesting statistics. In 2015, we didn't encounter any SS7 firewalls in our audits. In 2016, about 9% of networks had SS7 firewalls. In recent years, we have seen SS7 firewalls becoming more common. And what about diameter security? In 2015 audits, we didn't encounter any networks protected by a diameter firewall. The same was true in 2016 and in 2017 too. The first diameter firewalls in our audits appeared only in 2018. Overall protection of diameter networks is much worse than for SS7 networks. This is why intruders have focused on diameter networks. Now I will talk about attack cases that are feasible on mixed generation mobile networks. We have had the ability to recreate all these attacks in the wild during telecom security assessments. The first case is voice call interception, or MITM, on a combined 2G, 4G network. Firstly, I need to explain what a classic MITM attack on SS7 looks like. We assume that the intruder already knows the IMSI and address of the serving MSC. The attack consists of two steps. In the first step, the malefactor sends insert subscriber data to the MSC VLR node in order to spoof a billing platform in the profile of the target subscriber. Of course, the malefactor uses their own address for the spoofed billing platform. The MSC VLR node just answers OK, and the malefactor finalizes the transaction. The subscriber's profile is updated. To perform the second step of the attack, the malefactor should wait for the subscriber to call. This call initiates a request to the billing platform that has been spoofed by the intruder at the previous step. So the billing request in the initial DP message goes to the malefactor's equipment, disclosing the numbers of the subscribers involved in the call. The malefactor sends a connect message containing only one parameter, which is the number for call redirection. The intruder uses the number of their own private branch exchange. The MSC VLR obeys the command and redirects the call to the intruder's PBX. Then the intruder initiates the second leg of the call to the B subscriber, spoofing the number of the originating subscriber. They know information about the numbers from the billing request. After that, the call goes to the appropriate subscriber and they are able to talk. But what voice traffic goes through the intruder's equipment, where they can record the call or listen it in real time. An SS7 firewall can protect the network against such MITM attacks. When the hostile insert subscriber data message comes to the network, the porter STP sends it to the SS7 firewall. The SS7 firewall sees the operation code insert subscriber data. This is a category 2 operation, meaning that the firewall has to check the source operator and the operator of the target subscriber. What we see is a message sent from a Swiss operator, but involving the subscriber from a Taiwanese operator. Based on this result, the SS7 firewall blocks the insert subscriber data message. The network is protected. When the operator implements voice over LTE or VoLTE, the MME node handles subscriber mobility and the IMS handles voice traffic. In this case, even if the intruder succeeds with the profile change in the VLR database as the first step of the MITM attack, this does not affect voice calls via the IMS. As a result, voice over LTE indirectly protects the network against man-in-the-middle attacks. However, our intruder is quite experienced and has obtained access to both the SS7 and diameter networks. During the first step, the intruder needs to suppress VoLTE for the subscriber. They send a cancel location request signal message on the diameter protocol. This message is intended to prohibit subscriber services on the MME node. The MME implements the command and sends a positive response to the source node. After that, the target subscriber is automatically switched to the previous generation network. The previous generation network is based on SS7 signaling. To explain the attack, I have to talk about one interesting feature of the TCAP protocol. The component portion may contain more than one map protocol component. In this case, each map component defines its own operation, and subscriber identifiers in these operations might be different. When the SS7 firewall inspects such a double component message, it checks the subscriber's identity in the first component. Regarding the other data is a lone payload not meant to be inspected. Let's see how the intruder can use a double map component signaling message to perform a man-in-the-middle attack. They craft the double map message in which the first operation is insert subscriber data without a subscriber identifier. And the second operation is delete subscriber data with the target subscriber IMSI. The STP sends this message to the SS7 firewall, which inspects the first component only, determines that it does not have an identifier, and forwards the message to the destination. From the MSC and VLR's point of view, these two operations don't make sense. The node is being asked to simultaneously insert and delete data in the subscriber's profile. That's why the MSC VLR replies with an error message. If we pay attention to the details in this response, we find that the message type on the TCAP layer is continue. That means something like, I don't understand you, please repeat your request within the same transaction. The intruder proceeds with the transaction and sends one more double map component message. The first component contains an insert subscriber data operation without subscriber identity information. The second one also contains insert subscriber data with the target subscriber IMSI and spoofed address of the billing system. Of course, this address belongs to the intruder's equipment. The SS7 firewall inspects the first component only, after which it passes the message onto the network. The MSC VLR sends confirmation for both operations. That means the subscriber's profile has been updated. The intruder now just finalizes the transaction. Now the intruder is waiting for the subscriber to call. When the subscriber makes a call, the MSC VLR sends the initial DP signal message to the intruder's address inserted earlier. The intruder sends the connect message with the PBX's number. The MSC redirects the call to the intruder's PBX. After that, the intruder redirects the call to the B subscriber. The subscribers have a conversation, but the voice traffic goes through the malefactor's equipment. So we can see that even sophisticated attacks like voice call interception are possible on well-protected networks. One more case with voice call interception. In this case, the malefactor will attack a modern 4G, 5G network. The HSS contains HLR functions in order to be compatible with previous network generations, such as 2G and 3G. The intruder sends an update location signal message to register the target subscriber on a fake network. Note that the message comes from the SS7 interface. After a successful update location operation, voice services become unavailable for the target subscriber. When subscriber A calls target subscriber B, an SIP invite message comes to the IMS system. The IMS does not know where the call subscriber is located. That's why it sends location information request to the HSS. However, the HSS knows that subscriber B has been previously registered on a previous generation roaming network. The HSS sends a provide a roaming number request via SS7 interface to the node where the subscriber has been registered. This is the node of the intruder. The intruder replies with the PBX address instead of the roaming number, and HSS returns this data to the IMS in location information answer message. After that, the IMS establishes a call from the subscriber A to the hacker's PBX. What is the next step? the intruder could initiate the second leg of the call to the subscriber B. In this case, the IMS would request location information from the HSS, and the HSS would send a provide roaming number request to the hacker's SS7 node. The request would be looped. There is no way for the hacker to do that. Let's look at two options for what an intruder could do next. In the first case, the intruder sends an update GPRS location signal message on the SS7 network to register packet data service of the target subscriber on a fake 2G, 3G roaming network. During this operation, the HSS sends a cancel location request to the MME that makes packet data service unavailable for the subscriber. Now subscriber B is without any kind of mobile service. 4 and 5G mobile networks have an interesting feature. Mobile devices are in always connected mode. Signals from the mobile device come to the MME, but the MME clears the profile of the subscriber. This MME should restore the profile. It sends an update location request to the HSS, and the HSS sends the profile in the answer. Now the subscriber's profile is restored, and all services are up and running. At this point, the intruder initiates the second leg of the call. The invite request comes to the IMS system, and the IMS requests location information from the HSS. The subscriber has been registered again, so the HSS provides IMS with the real location information, and the call is established. Two subscribers are able to talk, but their voice traffic goes through the hacker's PBX. In the second MITM attack scenario, the intruder might take advantage of the connection to the Diameter network. They send a cancel location request message on the Diameter protocol just to the MME node. The MME clears the subscriber's profile. Now subscriber B is without any kind of mobile service. Again, the always connected mode helps to restore the subscriber's profile. Now the subscriber's profile is restored and all services are up and running. At this point, the intruder initiates the second leg of the call. The invite request comes to the IMS system. The IMS requests location information from the HSS. The subscriber has been registered again, so the HSS provides IMS with real location information, and the call is established. Two subscribers are able to talk, but their voice traffic goes through hacker's PBX. The third case is about money. If an intruder wants to steal money, they do not care about the target subscriber. The target subscriber can be any person. The intruder sends an update location message to a random subscriber with a random IMSI identity from the target operator. During the update location procedure, the destination HLR sends the corresponding MSSDN as a part of the subscriber's profile. Now the intruder knows the IMSI MSSDN pair. They generate a create PDP context request signaling message of GTP protocol that should contain both identifiers. This message initiates a packet data session from a fake roaming registration. The GGSN replies with the IP address for the user traffic tunneling. Now the hacker is able to generate any internet request as the victim subscriber. Since the goal of the hacker is money, they initiate an HTTP session to a server with premium content and create a subscription. The mobile operator assigns the subscription to the subscriber's identity as sent in the create PDP context request message. The more requests the intruder sends, the more money they earn. All these cases have been tested in the wild on real mobile networks during security assessments. Information about these attacks was reported to the GSMA Fraud and Security Group. The SS7 firewall bypass technique has been added to the SS7 Interconnect Security Monitoring and Firewall Guidelines issued by the GSMA Fraud and Security Group. The relevant vulnerability was reported to the GSMA Coordinated Vulnerability Program in December 2018. It has been assigned vulnerability code CVD 2018-0015. The main causes of signal network issues are architectural flaws in the protocols, mistakes in equipment configuration, and sometimes software bugs. On the one hand, most operators have learned to withstand SS7 threats connected with the first two factors. But software bugs allow an intruder to bypass security. On the other hand, most operators are still not protected against diameter threats. The thing is that, in most cases, the mobile operator can protect the network better without extra costs. They just need to check whether their security tools are effective against new vulnerabilities as soon as a new vulnerability is reported. We often see that hackers use advanced techniques to bypass protection and perform attacks. Mobile operators are also advised to use a signal intrusion detection system along with a signaling firewall in order to block a hostile source as soon as a threat is detected. Operators should configure their border security equipment carefully to block all known vulnerabilities. Afterwards, these three simple actions should be implemented as a constant process. This will help the operator to block hostile activity at the early stages. That's all. Thank you for your attention.